The Beef Value Chain Transformation, a data platform for standardizing and identifying trends in zoonotic diseases in beef production, by Mihle Senene and Omphemetse Tlakula. Our project leads, Prof. Wanda Mark-Otter and Haley Marcus, are interested in this pilot study in order to enhance the body of knowledge in the Department of Animal Sciences at UP, and they are interested specifically in developing a centralized data platform that integrates data related to foot and mouth disease outbreaks in South Africa, specifically in the beef value chain or in cattle. The current problem is that data is scarce, it's siloed, and it's inconsistent. This means that there are difficulties for stakeholders to be able to plan for recurring FMD outbreaks and to plan for the aftermath, such as trade, productivity in agriculture, and food security. And there isn't a centralized view at the moment where our project leads can go and see the current state of outbreaks and plan for the risks that are involved.
The objectives of this project is to maximize data integration, accessibility, and predictive accuracy by building a centralized data platform to integrate, standardize, and visualize datasets from across the beef value chain. The objective is also to enable spatial and temporal trend analysis of foot and mouth disease outbreaks and to develop a predictive model to forecast foot and mouth disease outbreaks using historical data. We received multiple silo datasets from our project partner, which we then integrated using districts as the common key. The master dataset then contained data related to foot and mouth disease outbreaks, such as the virus strains and the number of cases. We also included feedlot data and their locations, the types of abattoirs, weather conditions such as temperature, humidity, and rainfall, and we also included human demographic data. Our project approach follows the data science pipeline where we acquired the data. We then processed and cleaned the data by handling missing data and normalizing geographical data. We also added district coordinates to the data sets. We then merged the data sets using geographic and temporal identifiers. We then conducted an exploratory and spatial analysis to identify historical trends and spatial patterns. We then built a predictive model to forecast outbreak likelihood using logistic regression and random forest. We then developed our dashboard, which allows for data exploration, risk simulation, and trend analysis. Our dashboard is then deployed on Streamlit and it has multiple tabs.
During our data deep dive and analysis, we noticed that we had huge gaps in our data, specifically before 2020 and after. Before 2020, we had cattle heavy or livestock heavy data, and after 2020, we had abattoir heavy data. So we split into two models. The first model, pre-2020, brought the results that we see on the screen. We used random forest classifier to help us identify the top important features, and the results, for example, were wind speed and humidity. So on those two, they support the theory of how foot and mouth disease can spread, as airborne diseases can spread in long distance wind, and for example with humidity, if there are big herds such as cattle or sheep, that can also allow the disease to spread. The second model had much better results. with a balanced accuracy and rock worth of about 99.4%. And what's important to note here is the number of abattoirs also showing up on the feature importance. So seeing that we had very limited data, we know that this score that we see with recall also at 100%, it is worrisome. However, we had very, very little data that we were working with, and it would be best to test it further on unseen data when that does become available. All in all, pre-2020 model was highlighting the weather plus the cattle risk, and the post-2020 model was highlighting the weather plus the abattoir network risk.
FMD outbreak data and related factors is extremely scarce, and we also faced some privacy constraints. The data we did manage to receive also was a bit incomplete. We had missing outbreaks, and the years across the data sets was quite inconsistent. We also had some time constraint issues, as this project had to be completed within a very specific time frame. Recommendations for future work would be to close the data gap for the missing years between 2020 and 2021, so that there is no need for two models and just one model that is on a consistent timeline. The FMD outbreak dashboard consists of 4 tabs. Firstly, the map view, which allows the end user to view FMD cases on the South African map. It allows the user to also select a date range of their choosing, and then the cases are overlaid in red on top of the weather conditions. The one that's been chosen right now is temperature. The end user can also choose to overlay outbreaks together with the cases and on top of the temperature gradient. The dashboard also has a hover feature where you can hover over the cases to see more information about the cases, such as the district, the number of cases specifically, and the impacted species. You can also filter by province. As seen, the Eastern Cape has been selected. You can also select one or more disease type or virus strain. As seen, this virus strain is only found in Limpopo, KZN, and in the Free State. You can also select which type of species you want to see that are impacted with the foot and mouth disease. As you can see, you can hover over these. We also have the trends tab, which allows the user to view the cases, deaths, and kills due to FMD over time, and this tab also has the same filters as the map view tab. You can also select the type of avatar you're interested in, the type of avatar you want to see over time. And then we also have the forecast tab, which comes with a sidebar where you can simulate different scenarios to help prepare and plan for future outbreaks. You can toggle the number of abattoirs to see how that would affect the probability of an outbreak occurring. As you can see, you can also choose another year to forecast. Here we have selected the year 2025, which was not included in the historical data sets. And then we choose a different strain, which affects the probability of an outbreak occurring. For the month of January, you can toggle the temperature. So we picked a higher temperature because that is summer in South Africa, and we can see that the higher the temperature, the lower the probability of an outbreak. And then in July, winter, one of the coldest months, we choose 16 degrees, and we see that the probability of an outbreak increases to around 90%. You can also plan for higher populations in the year 2025. Changing the 80,000 to 800,000 does increase the probability to 71.6%. We can also filter by avatar type, and clearly the red meat or game avatar type has a higher probability. The forecast tab also supports month and district level forecasting, where you can select or plan or simulate scenarios for a specific district. Here we choose Buffalo City, and we can see that there's a 63% chance of an outbreak. When we select June, we have similar filters where we change to the year 2025 and the probability reduces. The last tab allows the user to download the full dataset that makes up the map view and trends tab.